All right, welcome to Honors Chemistry. We're looking at orbital diagrams, and our essential question is, what useful information can be obtained from an orbital diagram? So our orbital diagrams actually can be used to help explain some phenomena that we're going to look at when we are uh, in our future lessons and looking at periodic trends as far as atomic size, ionization energy, electronegativity, and then also electron affinity. That doesn't mean a lot to us right now, but these are a great model for showing why certain phenomena occur. So it's important that we know how to write them properly so that we can interpret them as well. So on our orbital diagram, it is just an orbital energy diagram is a type of notation which illustrates an atom's electron distribution and then also its spin within the orbitals. In our last lesson on electron configuration, we learned how to write the electron configuration. We need to be able to write our electron configuration with regard to uh, these orbital diagrams because they're really closely related. So I do want you to write an annotated, completed orbital diagram for magnesium, phosphorus, and calcium, and bromine. Um, and actually, we can show, yeah. Uh, Actually, we're going to scratch that part. We don't need to show an example of these. We're just going to show these rules right here. That's all I really want you to do. And so show the Aufbau principle, what is Hund's rule, and then also the Pauli exclusion principle. And then I'll go over how we explain unpaired electrons from the electron configuration of an orbital diagram. So we'll talk about that in just a second. But for right now, I didn't put in a template for an orbital diagram there. We are going to do some examples at the end of this lecture. So we can just leave that part out. So on this, when we're writing orbital diagrams, they just really are a way of showing electron distribution. Again, sort of like what we see with electron configuration. And so what an orbital diagram looks like is this, and we see we have energy levels, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. And we can see we could go all the way up to 7s or 7p if we needed to, but this one only is carrying us to 5p. But nonetheless, we see the energy increases as we move from energy level 1 to 5p. On this, here I'm showing a nucleus, and I like this picture because it also shows us, or it's just an illustration to show us that we do have the nucleus of the atom, and as we add energy levels, these electrons get further away from the attraction of the nucleus, which is something that we're also going to describe when we get into our periodic trends. All right, and we use Coulomb's law to help with our description there. So this is a depiction of that. Now we use in an orbital diagram arrows to represent electrons, and we're going to talk about this with these rules here in just a second. But an up arrow represents a positive spin, and a down arrow represents a negative spin. And so every time we have an arrow in our representation, those arrows are representing electrons. Now, when we have our quantum model, we end up with quantum numbers of the atom, and so this goes way outside the scope of our course, but we have these quantum numbers of sorts, the NLMS, and so we can see NLMS. So what we see is we have our principal quantum number, we have our L, which is our SPDF, we have our magnetic, which is some type of integer, and then we have our spin. Now, what we're really interested in with the arrows of the orbital diagram is this spin. And so we're interested in the positive spin being a half up arrow, or it can just be a full arrow, but generally represented with a half up arrow, and then the negative spin represented with a half down arrow. And so what we see there is that, and we're going to see this with our Pauli exclusion principle, is that we can't have an electron, or excuse me, two electrons with the same four quantum numbers in an atom. And so often we see that three quantum numbers are identical, and the only thing that's keeping them not identical is this spin. And so we're going to talk about what that is. So if we look at, for instance, a part here in 1s, we would say that we have an up arrow and a down arrow. And what we would say is both of these electrons, they have three of the four available quantum numbers in common. But because they have a different spin, that fourth quantum number is not the same. And that's really the only part of our quantum numbers that we need to pay attention to is the spin. And if you look at our orbital diagram, that's what we're really worried about here. We're well, not that, but we're interested with electron spin within the orbitals. And so these arrows represent that fourth quantum number either being positive or negative. But we know in a single orbital, or in a single box, if we will say, the electrons cannot have the same spin. Otherwise, they'd have the same four quantum numbers. And so I started off with that in this video, and I kind of ended like that in the lecture today in class. But now we're going to go through these principles real quick, and this is going to guide how we draw orbital diagrams. All right. So my first question is, what is the Aufbau principle, and show an example. And so the Aufbau principle, it says, our lowest energy principle says that electrons fill the lowest energy orbitals first before moving to higher ones. And so we can just use our example here. We can see, and again, this is the Aufbau principle listed right here. Lowest energy orbitals are filled first before higher ones. We notice in the anti-example, the one with the red X, that we have our two 1s electrons are filled. That looks good. But then we see that this 2s was not filled, and then the electrons were added to the 2p orbital before filling the 2s. That would make that incorrect. It would need to fill the lower 2s orbital prior to adding electrons to the 2p. And again, this violates a rule, but this also violates what we see when we observe electrons in nature. So just know that. So then if we look at the good example, we see that those electrons, same number of electrons, 4 electrons, those electrons are added to 2s, and then there's no electrons added to 2p because we don't have any more electrons. We only had 4. So we filled the lower energy levels before we started filling higher energy levels. And so the Aufbau principle just simply says we fill the lowest energy levels first, and then we fill the higher ones. All right, and this ensures that the atom's electronic configuration is as stable as possible. And then next we have Hund's rule, and it says when filling orbitals of equal energy, electrons will fill singly first with parallel spins before pairing up, and this minimizes electron-electron repulsion and contributes to the stability as well. So I don't know what happened there. All right, so we got the news for today somehow. All right, there we go. So we see on here that we have oxygen, and I'm not going to write this for oxygen. I'm just going to fill in what we mean by Hund's rule. So what we got on Hund's rule is if we have some electrons, and so we're following the alpha principle, we're filling 1s, and then we're going to fill the 2s, and then we're going to end up at 2p. And the reason why I'm filling these 1s and 2s first is to follow the alpha principle, but then I can't show Hund's rule in 1s and 2s orbitals. I can only show that when we get to 2p, 3p, 3d, 4d, where we have degenerate orbitals. What do I mean by degenerate orbitals? I mean these three orbitals right here, the sublevel, these are all equal energy. And so what this is saying is if I want to fill this 2p sublevel up, I need to fill these degenerate orbitals up with a single electron with parallel spins prior to the pairing up. And so now that they all had parallel spin, now I can add electrons. And so if that was 2p5, that would be a good electron configuration: 1s2, 2s2, 2p5. All right, but what would not be good is if I and this might be a little bit difficult to see, but if I did this number here, I know it looks the same that I drew it, but maybe if I did a 2p4, that would be a little bit better. But and the reason why I say that is it looked exactly the same, but there are times, and I'm not going to know whether you drew it properly or not until the end. There are a few configurations where I will know whether you drew it up, 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 and then down. So you can draw this wrong if you drew it this way, and this won't look the same. If you drew it up, down, and there wasn't a fifth electron, now I know you didn't fill this one with a single electron before they were forced to pair. And so I would know you're wrong. And this is what the anti-example is showing. All right, so the anti-example is showing that we have the electrons filled pairing up, but notice this one did not have one that filled singly first before those paired. That would cause that to violate Hund's rule. All right. Whereas we see in the good one, we see up, up, up. Now it's forced to pair down. And so it's very obvious with certain configurations, whether you drew it properly. It's less obvious with others, but if you just draw it properly, you won't have any problems getting things correctly. All right, so that's an example of Hund's rule, anti-example, one that's bad, and then also one that's good. And then lastly, and I've kind of front-loaded our instruction on this one, is the Pauli exclusion principle. And it says no two electrons in an atom can have the same set of 4 quantum numbers. This means that each orbital can hold a maximum of 2 electrons. And notice they have to have what? Opposite spins. Now, how do we show the spin of electron? We already talked about that. Electrons are represented with arrows. An up arrow represents a positive spin. The down arrow represents the negative spin. And if we notice, that is what we see with one of our quantum numbers, right? And so we represent the positive spin with an up arrow and the negative spin with a down arrow. And we always show the up arrow on the left and then the down arrow on the right. So that's something that we see. So what we see here in this anti-example is that both of these electrons have the same 4 quantum numbers. But because they both have on their 4th quantum number a positive spin, the other 3 quantum numbers are the same, but now this 4th one, they're both showing a positive spin. Whereas these have 3 of the 4 quantum numbers the same, but this 4th one, a positive and a negative. So it only has 3 the same, not 4. And you can have electrons with 3 of the 4 quantum numbers the same, but not all 4. And so we see this is a great example for following the Pauli exclusion principle. Okay, so let's go ahead and just do some examples because maybe we learn better just through examples. I know I do. And so I'm going to take you back. We'll do a retro lesson here. And we see that we have oxygen 18. Oxygen 18. Now, what do we mean by oxygen 18? And it seems like maybe forever ago we talked about isotopes, right? Just maybe it seems to you like it's been a long time, but here's our periodic table, and we know that oxygen 18 is just a simple isotope of oxygen. Whoops, something happened here again. I don't know what's happening. All right, so there we go. Just a simple isotope of oxygen. And so we see that oxygen indeed has an atomic number of 8, but this is oxygen with a mass number of 18. What does a mass number mean? If you remember, the mass number is the number of protons and neutrons in the atom, right? So it's the number of protons, mass number is equal to number of protons plus neutrons. All right, number of neutrons. All right, so we know that in the nucleus of the atom, oxygen has 8 protons because oxygen is defined as having 8 protons. Now, if we know the mass number is the number of protons and neutrons, and the mass number is 18, then we should have 10 neutrons. So I'm making us show in our orbital diagram the nucleus. What's in the nucleus are protons and neutrons, and then outside of the nucleus are electrons represented by our electron configuration, and in the orbital diagram, also their spin. All right, so what we see in oxygen 18 is that now we need to write our electron configuration for oxygen. So we notice on our periodic table that it's in energy level 2, and that it's in 2p1, 2, 3, 4. So we know we're at 2p4. If we follow our yellow brick road, and we talked about this in the last lecture, so get your yellow brick road out. We can go start at 1s2, 2s2, and then we would end at 2p4. And we notice that we have 2 plus 2, which is 4, plus 4 electrons, which is 8. So we have the right number of electrons for a neutral charged oxygen. So now all we have to do is show this in our orbital diagram. So we notice in energy level 1s, there are 2 electrons, and those electrons have opposite spin. So we show the first one on the left with an up arrow, the one on the right with a down arrow. We finished energy level 1 before we filled energy level 2, so we are following the off-bow principle. We go to energy level 2, and we're also following the Pauli exclusion principle because these have opposite spin, so they don't have the same 4 quantum numbers. So here in energy level 2, we're going to show our up spin and our down spin, again following our Pauli exclusion principle, and then and off-bow principle. And then we go to 2p4, and in 2p4 we're going to show up, 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 and then down. And so this would be our oxygen. All right. Now, how many unpaired electrons do I have in oxygen? So if we notice this, one of the things I asked you to answer, we see this one is not unpaired, and this one is not, this one is unpaired, and this one is unpaired. So we have 2 unpaired electrons in that orbital diagram. And so maybe you're asked something like that. You can tell the number of unpaired electrons by looking at the orbital diagram. It's real easy to see. Whereas you could not see that necessarily from the electron configuration. Let's go to another example, and that will be aluminum 26. So aluminum 26, we notice that aluminum is right here at 13, and we see that it is an energy level 3p1. So we're going to write everything up to 3p1. All right. So we'll start with the electron configuration here. So we have 3p1. Prior to 3p1, we have 1s2, 2s2, 2p6. How many electrons does that count for? 2, 4, 10, 11. All right, and aluminum has what? Whoa, that's not right. We did something wrong, didn't we? 1s2, 2s2, 2p6, Uh-oh, we left something out. What did we leave out? We got to make sure we follow our yellow brick road. 3s2, 3p1. So it's a good thing that we checked so that we know we have the right number of electrons. So let's count again. 2, 4, 10, 12, 13. Now we know we have the right number because we should have 13 electrons because we have a neutral charge on this aluminum. So we have neutral charge means we have the same number of protons and electrons. So since we know we have 13 protons in aluminum, we should show 13 electrons. So also we notice that this is aluminum 26. So what does that mean? We have 13 protons. How many neutrons do we have? Well, we should have 13 neutrons because 13 plus 13 gives us 26. And so there we're on our way with that. Now all we have to do is show our arrows in our orbital diagram. We start with the Aufbau principle with energy level 1, and then we show these electrons with opposite spin to follow Hund's rule, the Pauli exclusion principle. And then we go to energy level 2, go up and down. Energy level 2p, up, up, up. We're filling these singly first. Now they're forced to pair, following Hund's rule. And we're at 2p6. We go to 3s2, up and down, and then 3p1. So how many unpaired electrons do we have in aluminum? 1. We can see it right there very easily. All right, and so that is how we draw the orbital diagram. Of course, I added some things with showing aluminum 26. We showed the nucleus, and then we also showed all those electrons outside of the nucleus by energy level and then also by spin. So for now, thank you for watching. Please like and subscribe.